I'll start the 10th week of this course, and in this week you will see the common crystal structures. So it will be you will look at various crystal structures of elements, of simple binary compounds, and a few oxide compounds, and these are the common crystal structures that you encounter in lot of materials. So in a sense this will be fairly descriptive, and it will be nice to see how some of the concepts that we have talked about so far in this course they actually apply in the calculation of in the actual structures of different materials. So it will be in some sense it will be rewarding, because all this work we have done about structures and symmetry and packing and so on will actually be applied to see how to understand the structures of different crystals. Okay. And I will start this first lecture of the 10th week with a discussion on close packing and voids. And as I had said earlier, that a lot of crystal structure can be understood in terms of thinking of atoms as spheres which pack into space. Okay. So week 10, the first lecture, we will look at closed packed structures and voids. So what are closed packed structures? As we already learned, the FCC or the cubic close packed and the HCP, that is a hexagonal close packed, are close packed structures, and they have a packing fraction of 0.74, and that is the highest possible packing fraction if you have spheres. Okay. So if your atoms are perfect spheres, then this is the highest packing fraction that you can get. The body centered cubic has a packing fraction of 0.68, and the simple cubic has a packing fraction of 0.52. This is the monatomic BCC crystal. Okay. And similarly this is the monatomic simple cubic crystal. Okay. And as I had already said, that this idea of packing assumes that the atoms are spheres, and intuitively we feel that the most efficient packing should be preferred, because they would like to pack very closely to each other. Okay. So you might expect that most of the structures you will see are FCC and HCP, but the fact is that atoms are not spheres. Okay, and there are orbitals. Okay. So the bonding between atoms goes through orbitals, and there is a directionality in the bonding. So what we will see is that even though you would expect most of the atomic crystals to be FCC or HCP, we will find that significant number of them are BCC and other structures. So let's look at the crystals of elements. So I am just listing some elements and their crystal structures. So if you look at the cubic close packed or the FCC, you have copper, silver, aluminum, gold, nickel, lead. These are some of the metals that form a cubic close packed. The hexagonal close packed, you have beryllium, magnesium, zinc, cadmium, titanium, zirconium. These are just some of the examples. For BCC, body centered cubic, you have iron. Iron actually also forms an FCC, but at much higher temperatures, at more than 1000 Kelvin. Chromium, molybdenum, tungsten, tantalum, barium, these all form body centered cubic structures. Simple cubic, there is only one example of an element that crystallizes in simple cubic, that is polonium. There is a hexagonal structure, like for example graphite, carbon in the form of graphite crystallizes in a hexagonal structure. There are several tetrahedral materials. We have already seen the diamond structure of silicon or diamond, carbon or germanium. There are several others. Okay. Then there are some elements that actually crystallize in a rhombohedral structure, okay, with a space group R3m. So some of these examples are arsenic, antimony and bismuth. So this is actually the trigonal crystal system can have either the trigonal or the hexagonal, and you can have the hexagonal or the rhombohedral. Okay, so this comes in the rhombohedral crystal system. Okay, arsenic, antimony, and bismuth are some examples of this. Okay, so what you notice is that there is no clear trend. Okay, no clear trend. Okay, you cannot say that heavier elements prefer certain structures or something like that. We notice that arsenic, antimony, and bismuth, okay, are in the same period. Okay, so there is some similarity. For example, carbon, silicon, germanium, they are in the fourth row of the period, the fourth period, and they also have tetrahedral structure. Similarly, the rhombohedral elements are in the fifth period. Okay, and so there is some trends. Okay, some trends with periodic table. Okay, but it's not overall, there is no clear trend. Okay, and for example, there is no clear understanding of why iron is BCC whereas copper is FCC. Okay, and really these are just the crystal structures that are observed, and it turns out that the electronic structure of these elements makes them prefer a BCC. Makes iron prefer a BCC, whereas it makes copper prefer an FCC. Okay. Now, these are some of the crystals of elements. Now, one of the very useful concepts when you go to crystals of multi-element compounds, for example, binary compounds. Okay, what we like to think is that we like to visualize these elements as forming some crystal structure, and then the other element, okay, occupies some voids in that structure. Okay, so we will come to the concept of voids in the cubic closed packed structure. Okay, now here I am showing two layers, okay, of a cubic closed packed structure. Okay, so the black circles, this black circle represents the bottom layer, and the next layer on top is represented by blue. So these are atoms that form a cubic closed packed array. Okay, I am just showing two layers. Now, the difference between hexagonal and cubic closed packed comes in the third layer. In the hexagonal closed packed, the third layer is on top of the first layer, on top of this black layer, whereas in the cubic closed packed, it's actually in the it's directly on top of these green hexagons. Okay, so that's where the third layer will be. But we are just looking at these two layers. Okay, and what these two layers, if you just look at these two layers, we can immediately identify location of voids in cubic closed packed structures. Okay, so what we notice is that this black circle, okay, this black circle, okay, it is now imagine that it is at the center. It is at the center of 1, 2, 3, and 4. The three black circles and this blue circle. So it is right at the center of these four, and clearly it is in a tetrahedral void. So all these black filled circles, they correspond to tetrahedral voids. Okay. Now, there are other tetrahedral voids which are indicated by these red circles. Okay. Again, very similar to the black circles. Okay. The only difference is that in these red circles, okay, so there is one, they are directly on top of this black atom, and they are in the middle of these three blue atoms. Okay. So in a sense, the orientation of the tetrahedron around the red and black circles is inverted. Okay. So with respect to the black filled circles, okay, the orientation of the tetrahedron has three bonds going down and one bond coming up, whereas the red one has one bond coming has 3 bonds coming up and 1 bond going down. Okay. Again, please excuse the fact that I have not drawn these exactly. Okay. So actually these the location of some of these dots is not precise, but you can clearly make out where they should be. Okay. So we can immediately, what this tells you is that these tetrahedral voids are going to be there in any cubic closed packed structure, whether it is HCP or FCC. Okay. And similarly, the octahedral voids, okay, they will be located, okay, they will be located right here at the center of these 3. So if you look at this green hexagon, okay, now that is equidistant from these 3 blue circles and these 3 black circles. Okay. So clearly it is equidistant from these 6 circles, okay, and this is going to be a octahedral void. Okay. Again I should emphasize that this is actually below the blue atom. Okay. So it is in between the blue layer and the black layer. Okay. So the black layer, black open circles are the bottom layer, on top of that are the blue open circles, okay, and in between those two, right at the center, right here, there is a octahedral void. There is an octahedral void, and due to periodicity it is there in all these locations. So what this shows, okay, is that you can immediately identify the tetrahedral and octahedral voids in both an hexagonal closed pact and a cubic closed pact. Okay. As I said, a cubic closed pact, the third layer will be directly on top of these hexagons. In a hexagonal closed pact, the third layer will be directly on top of these black circles. Okay. However, let's I mean, and so also we should keep in mind that for cubic closed pact, okay, the closed pact direction is actually the 111 direction of the crystal. That means this screen, okay, screen is the 111 plane. Okay, so that is the closed packed direction. Okay, and you can easily take a cubic closed packed or an FCC structure and see this packing arrangement. Okay, and what it says is that you know, whether you have an FCC or an HCP, you can identify the location of the voids. Okay, and this is very useful. Okay, and if you go back to the lectures where we discussed the location of voids in HCP, you can go back and confirm that these were indeed the location of the voids. Now, what is interesting about these voids is that these voids, okay, are spaces where you could in principle fit atoms. Okay, but if you wanted to fit an atom in a void, you need to know the size of the void. Okay, and again, so we are going to do some calculations on with respect to the size of the voids. Now, let me emphasize one point which might not have been clear. Okay, is the following, that you know we usually show the FCC structure in the form of a cube. And so we usually show it in the form of a cube, and we show the location of the voids. Okay, so the tetrahedral voids, as you are familiar, will be located along the body diagonals, along each of the body diagonals. So there are 8 tetrahedral voids located along each of the body diagonals. I am not focusing on the sign of these tetrahedral voids. Okay, but you know that there are 8 of these located along the body diagonals. Okay, these are, what I want to emphasize, that these are exactly the same as shown here. Okay, there is no difference between what is shown in this diagram and in this figure. Okay. So, the tetrahedral voids exactly the same locations that are described here. This is just a different way of looking at the structure. In fact, you are looking at it from the 1 direction, okay, which is which can be shown as let us see, if we take this as the origin x, y, z. So, we can take this as the 1 direction, as a 1 plane. So, actually the screen corresponds to this plane, okay. And if you look in this plane, then you will see exactly the structures that we are seeing here, okay. And now if you go to the layer below this plane, okay, then you will see the packing arrangement that is seen here, and you can you can immediately identify the tetrahedral voids, and you can show that what you see in this figure is the same as what you see here. Similarly, for the octahedral voids you know are located at the edge centers and the body centers. So, there is one right at the body center, that is an octahedral void. I will use the green color, and located at each of the edge centers. Okay. And again this is exactly the same that you see in the other figure. Okay. And until you draw it and convince yourself, okay, you won't be sure of this. Okay. So, these two are two different ways to look at the cubic closed packed structure. Now, let us calculate the radius of these voids. Now, to calculate the radius of the voids, okay, I will start with the cubic closed packed, but it is the same for the HCP. So, if you look at a cubic closed packed, now for the tetrahedral void, we know that so you have so now the tetrahedral void is located along the body diagonal, and it is located at 1/4 at 1/4 of the way along the body diagonal. Okay. So, I will just show a tetrahedral void here, and along the body diagonal, okay. So, if this is the corner, and let us say this is the tetrahedral void, what you have is something like this. You have your sphere, which is the atom, and you have the void, okay. And you know that this distance is a root 3/4, and that is equal to r of the atom plus r of the void. Okay. And now r of the atom, okay, this again let me remind that r is the radius of the atom and a is the size of the cell. Okay. Now, so r of void is equal to a root 3/4 minus, now r of the atom. R of the atom can be related to the lattice parameter, because along the face diagonal, okay, you have a root 2 equal to 4r. Okay. So, r is equal to a root 2/4. Okay. So, then I can write this as a root 2/4. So, you get the size of the tetrahedral void, a times root 3 minus root 2/4. Okay. So, this is the radius of the tetrahedral void in terms of this in terms of the cell parameter A. Okay. Now, this is the radius of a tetrahedral void, okay, in a perfect assumes atoms form a perfect FCC. So, in the sense we impose this condition, okay, which is only true if the blue atoms form a perfect FCC, okay, and then we use you use this condition to find the size of the tetrahedral void. Okay. Now, what I mean is that if you actually squeeze an atom, okay, then the FCC might get distorted a bit, okay, but still for in a perfect FCC this is the size of the void. Okay. Now, interestingly you can ask what is the ratio of the radius of the void to the radius of the atom. Okay. So, this is root 3 minus root 2 divided by root 2. Okay. So, this is the ratio of radius of the void to the radius of the atom. So, all I did was take the radius of the void divided by the radius of the atom. Okay. So, this is for the tetrahedral void. Let me put a T in front next to the void. Okay. So, this is for the tetrahedral void. You can do for the octahedral void. Now, for the octahedral void, okay, again you can just go along the edge, okay, and you can easily calculate that. So, for the octahedral void you have radius of octahedral void plus radius of atom, this is equal to a by 2, okay. And so, you can immediately see that the radius of octahedral void is equal to a by 2 minus a root 2 by 4. Okay. And further you can also do the same. You can divide by a root 2 by 4 to get the ratio of radius of octahedral void divided by radius of atom. This is 2 minus root 2 by root 2. Okay. So, we can work these things out, and these are useful relations. You can do the same for hexagonal. Okay. You can, if you want, you can start with the HCP structure and you will get essentially the same result. Okay. So, the size of the voids, okay. So, what this says is that you can fit another atom of this size. Okay. But now, if you calculate these fractions, okay, so this is of the order of okay. So, this is only about this is less than 25%. Okay. So, what this says is that the atom that you can fit in the tetrahedral void has to be extremely small. Okay. Has to be extremely small, okay, if it has to fit, and if it has to fit in the tetrahedral void and keep the structure intact. Okay. And clearly that seems very unreasonable. Okay. In fact we will see structures like the zinc blend, okay, where the atoms fit in the tetrahedral void, but the size is a lot more. Okay. Size is not, the ratio of sizes is not this small. Okay. So, that is what I meant by saying that this is in a perfect FCC, but there can be distortions. Similarly, this is about and this is about this is much higher. Okay. So, this is nearly about 0.43. O2, okay. And yes, I mean this is significantly larger, okay, but still it is much smaller than what you would expect. Okay. So, this is about the size of the voids. Okay. Now, let us look at something that that we sort of skipped when we did the hexagonal closed pack structure, and this has to do with an ideal hexagonal closed pack structure. Now, what do I mean by an ideal hexagonal closed pack structure? Now, let me draw the hexagonal closed pack structure in the way that you are used to seeing. Okay. So, this is where you show a hexagonal structure, okay, and what you have is you have these atoms here, okay, and you have the next layer, okay, which the layer below you will have three atoms, and then you have another layer below where you have 6 atoms, 6 or rather, okay. And now the reason I am showing it this way is the following, that that this distance in a hexagonal, in a HCP, this is called C, okay, and this lattice parameter is called A. Okay. Now, if you take a unit cell of this, okay, what you will see is the following, that let me draw it in the following way. So, you have A, B, C. This angle is 120 degrees. Okay. And now the question is, if you have an ideal HCP, okay, then it turns out that there are some further constraints. Okay, C has to be related to A. Okay, C is not completely independent of A. Okay, so so this side is A and this side is C. So there are two parameters. Okay, so you have A equal to B and gamma equal to 120, alpha equal to beta equal to 90. Okay. And in an ideal HCP, okay, now there is going to be one other atom that is located right here, okay, inside this cell. Okay, it is not right at the center. Okay, it has to form a, it is located in a, it is located in this, it is located at the center of these 3 atoms. Okay. So, what this tells you is the following, that this distance, okay, in an ideal HCP should also be A. Okay. So, if it was perfectly close packed, then this distance, this diagonal distance should also be A, this distance. Okay, let me show it in red. Okay. So, this is from this corner to the center of this atom. Okay. So, that distance should also be A. Okay. And it turns out that this, so you immediately have a relation. Now, now you know that this is related to C in this way. Okay. And so you will get a relation between C and A. Okay. Now, let us work out that relation. Now, you can let us see the location of this atom. Okay. And for this, let me use the planar representation. So, in the planar representation, okay, I have okay, so I have these 4 atoms located here, okay, and then I have this center atom is located at height c by 2 along this. Okay. So let me, these are all at z equal to 0, z equal to 0, and this is located at z equal to half. Okay. And you know that this distance is a, z equal to half or c by 2, more like c by 2. Okay. So now let us look at the coordinate of this atom. So the coordinate of this atom in blue, this equal to, so let me make a choice of the origin. I will choose A, this is my B. Okay. So the coordinate of that is clearly the x coordinate is 0, it is located right here. So the x coordinate is 0. The y coordinate, okay, y coordinate, now in order to find the y coordinate you have to find this distance. Okay. And this distance can be found out from this angle. Okay. So this distance can be found out from this angle. So it is a by 2 divided by cosine of this angle. Now cosine of this angle is root 3 by 2. Okay, this is a 30-degree angle. So the cosine of that is root 3 by 2. So this is equal to a divided by root 3. Okay, so the y coordinate is a by root 3 and the z coordinate is c by 2. Okay. So now if you take a distance from the origin of this point, and the origin is located at one of these, origin is located right here. Okay. So now if you take a distance from origin, okay, then you can immediately find the you can say that a square by 3 plus c square by 4, okay, that is the distance of this blue point from the origin. Okay, this should be equal to a by 2 square, a by 2 is square is sorry, it should be a square. Okay. And this immediately implies that c square by 4 is equal to 2 a square by 3 or c by a is equal to square root of 8 by 3. Okay, and this works out about 1.63. Okay. So this is the ideal ratio for a hexagonal close pact. So if the atoms were really close packed, then the c by a ratio would be exactly 1.63 in a hexagonal close packed structure. Okay. Now let us look at an ideal cubic close packed structure. As I had already said, in an ideal cubic close packed structure, the face centers, okay, should be touching each other. So let me again draw this. So we just take the planar representation. Okay. Now it should be such So in an ideal cubic close packed structure, you should have now you have only one parameter A. So A root 2, okay. So this distance, which is A root 2, should be equal to 4 times the radius of your atom, okay. And so this is an ideal cubic close packed structure, in the sense the atoms in blue are forming a perfect close packed structure, okay. So interestingly, unlike the hexagonal close packed structure where we had a parameter C, okay, in this case there is no additional parameter, okay. And again this is just a convenience of notation. I mean, if we had directly imposed the condition for ideal hexagonal close packed structure, in that case also we would not have any independent parameter C. C would be equal to A into root 8 by 3. Okay. So with this I will conclude this lecture. I will conclude this first lecture. So here we have seen the idea, how the idea of close packing can be used to understand the sizes of voids, and also we saw the structures of simple elements. Now in the next lecture I will look at binary compounds and see how these can be understood in terms of close packed structures and atoms in voids, okay. And we have already seen this in several examples, like the most common example that we see are the rock salt and the cesium chloride, okay, or the zinc blend structures, okay. So these all can be understood in terms of one of the elements forming a close packed structure and the other element in a void. So we will look at this in more detail in the next lecture. Thank you.